So I'll continue this workshop and coming back to talk again about more of modeling, and especially using the WRF. And so in this presentation, I'll try to explain you how to use, how to evaluate the model. What do we need to think about evaluating the model? So we have a simulation, and what to do with the simulation to check if it's a good simulation or not, which errors we have to think, and this kind of things. So first of all, the question is, why do we need to verify? When we verify a model, we just verify a model because we disagree with a fact. So, for example, you have to create an hypothesis, and then you disagree with something of the model. So, for example, I run a model and operationally, and I realize that something is going wrong, and so I disagree with the model results. And then I elaborate an hypothesis for that. I create and then I try to prove, and then I develop an improvement. And so, for example, I run a WRF for 3 months on my hometown, and it was underestimating the rainfall. And this is like, I'm going to tell you a true example that happened to me. And so the fact is the model simulates rains within an accepted error, but it does not. So what I decided to do, I decided to change the cumulus parameterization of the model, since I verified that the problems were occurring during convective days. So first I have a fact. So the fact is the model simulates right the rain. And then I disagree with that fact because I realized that it was not estimating the rain. Then you create an hypothesis. So my hypothesis is the cumulus problem with some cumulus parameterization. So why of this? Because it was happening during convective rains days. So it was on the cumulus parameterization. So the problem is in cumulus parameterization, and the proof, I simulated the model with other cumulus parameterizations, and then I checked that with another cumulus parameterization, the model was doing a better job. So I changed it from, I was using, for example, the Chich cumulus parameterization. I changed it to Kain-Fritsch, and then I verified an improvement on my weather forecast. And so this is the development part. So basically everything that we do with a model when modeling and verifying is this. We disagree with something that is going on in our operational forecast. We try to elaborate hypothesis why it's not going well, and then we try to make an improvement and verify that improvement. I told about error. So what is an acceptable error? Because you have to define. Error is something complicated for meteorologists. So what is an error? An error, like for you, this can be just something, maybe some animal, or I don't know, a dog, a kid draw. When you get more resolution, you start to see more details, and then you can define, okay, this is not only a geography picture, it can be, I don't know, a dog. And then you go more resolution, okay, it's a car. you can define. And then you go with more resolution. Okay, I can see the hair of the car, the details, and for some people this can be a car. For an engineer, this can be a car. For an architect, this is not a car. This is a car. But depends on the how do you accept your error? What is important for you? So it's the same in meteorology. We have to know, is it telling it's going to rain or now it's raining? So as like a meteorologist, I said, it's raining. Is it, am I right? Or should I say it's raining 20 millimeters at 2:38? The interpretation can be different. And with more accurate is your like the more the error should be lower, more physics you have to take into account. So depending on how high is your I forgot the word, but how low you want your error, you have to decide for different parameterizations in the WRF model. So with that example of the car, we think about resolution. So which resolution am I going to use? Then you have to think about a wave. A wave, because model solves waves. The model, everything about meteorology is solving the wave equations. And then if you have 2 grid points to solve a wave, your wave will not be a wave, it will be a straight line. If you have 3 grid points or 2 boxes of a model, you still have a straight line. With three boxes, you can have something more like a wave. And with 4, then it's more correct. And with 8 is, we model, people who work with modeling, we say that we need at least 8 grid box to solve our phenomena. So for example, a sea breeze occurs not in some places with 80 kilometers. So for solving the sea breeze, we need at least 10 kilometer grid spacing. Like here we need to solve the Seychelles Island. We need at least 8 grid points to well solve the Seychelles Island and all the waves that are created by the island. And for example, I took an example as an island we have in Brazil. The GFS model, this is the topography file with 0.5 degree resolution. It doesn't see the island. It's sea, there is no island. With 27 kilometer resolution, nothing happened to that. The model cannot see the island. With 9 kilometer resolution, the model can see a peninsula, maybe, but still not an island. With 3 kilometer resolution, then we can see the island, and then we have more than 8 points here. And so if I want to solve, make a weather forecast for this island, I will need at least 3 or 1 kilometer resolution to solve. But then we go in the theory that, okay, so is it better to always improve? So why, if I have unlimited computer power, why don't you go to a 10-meter resolution model? Then we have the problem of the core, because when we solving like 10-meter resolution, I have to solve each hair of the car. So I have to solve the physics involved. If I don't have good parameterizations, it's better to stay with lower resolution, because the physics here is much easier than the physics here. So you have to think about changing parameterizations to when going to lower resolution. Read on the manual. Sometimes in the manual we have it explains, okay, this parameterization is better for high resolution. You cannot use this parameterization with lower than 1 kilometer. You have to turn on a large edge simulation instead of PBL scheme for the model to solve. And also, it's not only about the horizontal resolution. You have to think about the vertical resolution of the WRF. We can set on WRF, maybe I'll show you today or tomorrow, how to set up the vertical levels in the model. And it's really critical. Its vertical level is as critical as the horizontal. If you set a lot of levels, you asked in the yesterday about you verify that putting more levels in high in the stratosphere, you changed the rain in nears here in the troposphere. It can happen a lot of things, because the model has a default how to distribute the vertical levels. And if you put a lot of levels, it can, near to the surface, be too close the one level to other, and then you create some problems. You go to the problem that your grid box is too small, and many things can happen. So horizontal resolution and vertical resolution is something you have to take care when modeling. Another thing is, now let's keep the same resolution and compare two domains. So thinking about the domain size. Here we have an example from the Warner book. It's a book from in the course, web course from Michel Mesquita that we are following. He asked us to read this book, and this is a picture from the book. He provides also in the web page a version from the book, an online version. And here, for example, we have a larger domain and a small domain, both with the same resolution. And what happened here is that when the borders, lateral boundaries of the model was far, he solved a jet stream. This is wind. He solved well a jet stream. When the boundaries was close to my interest area, it didn't solve the jet stream, although the resolution was also 40 kilometers here and here. So it's important, I told you yesterday, to make big domains. If you make small domains, although you make a high resolution domain, it will be very similar to your input data, for example, the GFS. You will not get any advantage of running WRF if your grid is too small. So the first domain, at least, it has to solve the synoptic conditions, and the domains have to be large enough to solve, for example, the subtropical high pressure or the low pressure systems that get inside your domain. And pay attention, where are you going to simulate. So for example, this was a jet stream that comes from here. So you are not going to put your interest area here because everything comes from the north, as I explained you yesterday. Let's switch all the domain a little bit up to solve better this jet stream. And so your domain not necessarily is going to be in the middle of the grid. Can be like from domain like this. I would say that would be like here is the best, the point of interest. And I'm going to talk about another kind of error. I told you about the error about setting the domain, setting the resolution, and we also have to be aware of computational errors. What is computational errors? When we think about computational errors, at least me, I think about the chaos theory from Lawrence. Chaos theory is the butterfly effect. So it's like the flap of a butterfly wing can make a tornado somewhere. And well, it's not really like this, but the idea behind is that let's suppose a perfect model in terms of physics and initial conditions. If the forecast, although it's a perfect model, we see that the forecast will not be perfect due to truncation errors. And because of the nonlinearity of meteorological equations, small deviation may increase significantly the error during the weather forecast. So for example, a simple equation, so this is a trivial equations like the next time step of a variable x is equal to an equation, and after 15 time steps, the solution will be completely different. If I, like the blue, there is no truncation, and the red, I make a truncation in the 1, 2, 3, 4, 5, in the 6 decimal case. And the solution went from 0.1 to 1, and in 15 time steps. And it happens with models. Lawrence realized that in his experiment, he ran a model, and something went wrong, that he lost his simulation. But he said he could recover his last file, his picture. And then he went to another machine and trying to run the model with the same setup, but the simulation went to a completely different result. And then he developed this theory about the chaotic theory because of the truncation of the machine. One machine was with like 15 bits and the other 16 bits, the other with 24 bits. You'll have different weather forecasts. So if I run the WRF here in my machine with 64 bits, and you run in your machine with 32 bits, we will have different weather forecasts. They will not be the same because of truncation errors. Okay, truncation errors, and resolution and setup errors. Another error that we have to be aware is initial condition errors. We have to know that analysis, they are not perfect. And for us to know that, we have to understand how they are created. What is an analysis? Analysis is, it's not only grid interpolation, but it's a kind of interpolation of observed data, but together with model. So first you have your data observed by ship, satellite, and a lot of sources. And then what the operational system they do, they run a model, and for example, we are going to make the analysis for now at 2. and I get the last run that I did this morning. I run the model for from at midnight I run. I get the forecast for now 2 p.m. and then I have a map. I compare this forecast with the observations, and then I try to make a map with the difference between them, and then we add this difference on the simulation, and then we make a cycling to make the analysis, to build the analysis and then start a new forecast for the next time we make another analysis. And this is analysis. So analysis is not only interpolation of observation. It's a product of observation plus model simulation. And observations, we have lack of data. We have a lot of observational problems. And also the problems, they have problems with physics because they don't solve like the butterfly or everything that happens. They have a limited resolution. So making a summary, this figure is also in the Warner book. We can think about a theoretical limit of the perfect weather forecast. The perfect model will not be 100% accuracy during the time. It will decrease. First, it will decrease because unsolved physics. Although the physics are perfect, you have problem of setting up the resolution. You can go to 50 meters resolution. I'll tell you that there are physics that happens in the molecular and you are not solving. So then it's always impossible. You have to go deep and deep in resolution. There will always be an error here in the beginning. And then you have problems with truncation that will make your simulation blows. Accuracy go down. And for the real dynamic models, what happens, it will start with a low accuracy. Why? Mainly because of your analysis. Because you start your first time step, it's your analysis. And your analysis, because all those problems that I told you before, they are not completely perfect. They are not a reality. So we start with a low accuracy. Mainly because it's from a low resolution model. For example, analysis of GFS or analysis from ECMWF. And then you start running your high resolution model, and you see that the accuracy, your model error will be lower, so the accuracy will be high. It start increasing. And it will increase until it stabilizes and then start decreasing again. Your error will start to increase. This time between when start increasing the accuracy and then going down is we call more or less for it's the spin up time. So the model has a spin up until it's stabilized. Usually this is about 12 hours, from 5 to 12 hours that you throw away your simulation. If you compare to an extrapolation algorithm, what is extrapolation algorithm? It's, for example, it's nowcasting, what we do with radars. So you see the hurricane coming, and then you extrapolate the trajectory of hurricane based on velocity. So you start with a high accuracy and then go down. And then we have to compare the data from the model with the data observed to prove something or to verify the model. We have to keep in mind that the observed data Carolina told you, there are problems with observed data that we have to. They are not absolutely the truth. They have problem with gaps. They have instrumental problems, and so we can't not completely know the reality. But although we have to work with what we have. So just to keep in mind that you must be exigent and be tough about your comparisons. For example, the observations, sometimes the model, because of the resolution, the model simulates a hill with 20 meters high, and you have the real hill is 100 meters high, and then you have an observation here, and at 10 meters, and it will measure a wind. And in your model, the 10 meters will be down here. Then it's measuring the arrow number 2. So the model is not wrong. The wrong is where you are comparing your observation. And how to compare? There are thousands of algorithms. The algorithms that Carolina presented you, and for comparing model with observations. And there are also these dichotomous evaluation, which is quite simple to do, quite easy. And for operational system, it's so. For example, I want to evaluate the tornado forecast, or you can make a table with yes or no, and yes or no for observed, and then you just count how many times you forecast well the tornado, and you said yes, and it was really observed, and you said no, and it was not. And then make some, for example, the probability of right tornado forecast is 60%. The percentage of correct forecast is 97%. So after 1 year working with that, you can create a simple table like this and get information to develop your hypothesis. The model is not my forecast is not forecasting tornado or forecasting other variables. You can do it with rain and set up thresholds. For example, for temperature, temperature less than 20 degrees Celsius or rain more than 20 millimeters, you set the threshold of your error, and then you create this kind of tables. And then there are a lot of indices that you can create with the table. So if you define the value here is A, B, C, and D, and here will be A plus C, B plus D, and the total, whatever you can decide, define objective values to evaluate your model based in a simple table that can easily be done. And Carolina showed you a software, and there is also another software from Matt, which is from the NCAR. It's from the NCAR, this software was made also to evaluate the worth model against observations. And there are a lot of descriptions in this web page that you can, I really recommend you to check this web page once in a life, because there are a lot of tools that can help you. And this software, it's another model. So it gets observations and analysis, ensemble data, model from worth, and then create pictures and ask file for comparisons. Now, and you can, in this page, you can download observational data from reanalysis, from the TRIM, from satellites. Everything is there in the web page that you can download and to compare with your model simulation, and then create hypotheses. Where is your model doing well and where is not doing well? Well, this is like an introduction about modeling. I think we could continue with what we were doing yesterday, and I think
have a short break.
yeah, we can make a 10 minutes break.